Hello everyone, and welcome to yet another recreation programming session with Mr. Zozin. On the previous session, we started to develop a 3D game, a software rendered 3D game. And what we did, we actually ripped off the 3D rasterizer from our library called Olivets, and put it into a simple X11 application. So this is how it looks like. And on this specific distance from this Utah teapot, it already performs at 60 FPS. This is 60 FPS. If this number is below than 0.16, right, 16 milliseconds, it's already at 60 FPS. So this is already at 60 FPS. But do not take too close, all right, because... So I very strategically actually put the camera a little bit away from the Utah teapot, so for the demo purposes, but in any case, I didn't even put any optimization on this entire raycasting, not really raycasting, but rasterizing, so it's totally fine for it to be slow for now. But later we're gonna try to improve it. So, and when I was playing with this specific rasterizer, it was kind of obvious that it was not designed for making a game. What it was designed for is for making demo for the library, right? So let's take a look at that. So how the demos look like. So here are the demos for different things, and specifically we have a Utah teapot in here, right? So that's the demo. And as you can see, camera, you can't move the camera in here. So the camera is absolutely static. And because of that, I actually took a bunch of shortcuts in here, which are not really acceptable if you're making a game. So, and what I want you to do today is to maybe fix some of those shortcuts, right? So, and some of the bugs and stuff like that. So specifically, we'll need to probably work on near plane clipping. So essentially, usually for this kind of games, right, so you don't really render everything. If something is too far away, right, you kind of clip that. So you probably noticed that in 3D games, right? So there's some sort of like a far clipping plane, and here you can observe the effects of the far clipping plane in here. So it's just clipping this entire stuff. Actually, on the level of fragments, we're using the depth buffer, right? We're using a depth buffer which keeps track of the Z value of each individual pixel in here, and this is how we're able to actually clip some of this stuff, right? But so the near clipping plane, the one that clips when you come to the object too close, is not really working currently correctly, right? So in fact, it's not even implemented at all, right? So if I try to, for example, this is a floor, right? So I try to put like a rainbowish triangle on the floor because we're definitely going to have some sort of a floor, right? So the player or the character has to stand somewhere. So, and I was testing that. So if you try to sort of like penetrate it like that, something really weird going on. And moreover, like the colors at some point starts actually going like completely haywire. Like, what the fuck is this? Like, what the fuck is this shit? And it's just like, it's not, the clipping here, as you can see, not even working. Like, what the fuck is going on here? And it's just like, thank you. It's a pretty cool teapot. So there's something definitely wrong with the near clipping plane. The reason there's something wrong with the near clipping plane is because you have to geometrically clip things. If in case of the far clipping plane, we can just keep track of the Z values of each individual pixel and just don't render those pixels when they are too far away. In here, we actually kind of have to modify the mesh. Right, so to understand how all of that works, we probably need to draw like the way we project 3D objects onto the 2D screen. Right, so let's go back to the basics. So I hope it's going to be more or less convenient for me. So it's kind of difficult for me to hold the pen, but I'm going to try my best. So here you have an eye. This is your eye, or maybe we can call it a virtual camera. So, and you have the axis, right? So the one axis goes somewhere to the right. Oh, I didn't want to do that. What the fuck is going on? Right, so goes to the right, and another one goes up. Something like that. And let's say that this is an x-axis, right? So this is an x-axis. Maybe let's say it's y. I think it's going to be better to call it y, and this one is going to be z. Maybe, okay, so if I call it x, what does it mean? It means that I'm looking at the scene from the top, right? So I'm looking at it from the top. So X is going somewhere here, right? So this is Z, and Y is actually looking at us, right? So that's what's going on in here. So, and imagine that you have some sort of like a object in 3D space. It is 2D space, but we do that in a 2D space to simplify the whole thing, right? So we're just simplifying the whole thing, essentially. And how do you even display it in 2D space, right? So you have some sort of a notion of the screen, right? So here is your eye, and here it is behind the screen. Here it is behind the screen. And what you do is just like you tracing a ray from the point, from the vertex to your eye, and the intersection with the screen is the coordinate of the point that you have to put on the screen. It's actually that simple. It's actually that simple. We already actually looked into that in Olivet's series, right? We already looked into that. So people who watch that probably know exactly what I'm talking about in here. Right, so there is nothing particularly special here. So this is a P1 prime, right? So it's projected, and this is P2 also projected. So there's two of them. So computing this kind of stuff is rather easy. So if you imagine that P1 is X1 and Y1, right? P2 is X2, Y2, and P prime 1 is X prime 1, so on and so forth, right? So I'm not going to like write all of that down. So this is basically the convention in here. Right, so the way you do that, right, so you may think that you have some sort of a triangle in here. So this is the axis, one of the Z axes in here. And in reality, what you have in here is this sort of triangle. So this is the first triangle, right? So this is the first triangle. And this is a smaller triangle. This is a smaller triangle. So the position of the screen, you can put it as S, and it's a Z value of S. Right, so essentially, since it's two similar triangles, right, so it's two similar triangles, the relationship between X1 prime, right, so the X of this thing, and its Z value, which is called S, right, so that specific S, is equal to the relationship between X1 and its Z position, which you also know. Which is going to be, I just realized that this has to be called Z, I'm sorry. Right, and it's Z in here. So, and if you shuffle things around, right, so if you effectively shuffle things around, you will come to a conclusion that to find this specific coordinate, you have to do X prime 1, just divide X by Z, right, divide X by C and multiply by the distance to the screen. And usually for the simplicity, we assume that the distance to the screen is equal to 1. So what you end up with, is that you have to take X and divide it by Z. So if you have 3D object, the simplest and easiest way to perspectively correctly project that 3D object onto the screen is take its X, Y, Z, take X, divide by Z, Y, divide by Z, and you have X and Y on the screen, and you automatically have a perspective 3D. This is the simplest formula that you can even derive yourself. And I really have like warm memories toward that formula because I learned it when I was 18 or 19, just accidentally learned it. I tried it out in, I think, Visual Basic at the time, right? Visual Basic, and it just worked. And I was just like, holy shit, I can do 3D that easily? Holy fuck. So, is S called FOV? No, FOV is actually field of view, and it's usually measured in degrees. You have to derive degree of field of view from the distance to the screen, right? So in reality, usually when you have this formula, you have to compute it in terms of a distance to the screen from the eye. And FOV is something that we created for humans to kind of vaguely estimate what that distance means, right? So because if you, in your settings for the player, say, here is the distance from your eye and the screen, what the fuck does it even mean? It doesn't make any fucking sense. It's only for computation. So FOV is something that we came up with to put in a setting for the player so they kind of understand what the fuck we're talking about, because the distance affects the field of view. So the closer the screen, the more field of view you have. The farther away from the screen on which we're projecting, the less field of view you have. Right, so that's what it is. To compute the field of view, I don't know how to do that, right? So I will have to derive the formula, and that's kind of besides the point what I'm doing right now. So people say that I avoid the floats. I do use floats in some of the situations, but I do want to avoid them at some point, right? So I do avoid them, but there's a little bit of a floats computation in the game right now. So anyway, but here's the thing. What if the point that you're trying to project is going to be actually behind the screen right in front of you, essentially somewhere here? So what's going to happen? So this one is rather interesting. Maybe this particular point is not great. Let's put it somewhere, I don't know, here. So here is the point. So you can ignore it, but you can try to project it. In fact, if you literally use the same formula, you're going to end up with literally the same situation. Is just the projection is going to be here, right? So that's the point P3, and that's the projected one. So they kind of switch places, and effectively the closer the point is, even if it's already behind the screen, the more towards the edges of the screen is going to go, and this is what contributes to the fisheye effect that sometimes you see. Right, so I can even demonstrate you what I mean by that. So if I get too kind of close, there is a little bit of a fisheye effect going on with the teapot. Can you notice that? Right, can you notice the fisheye effect? So that's basically already some of the points behind the screen, and they're sort of like bulging out. So that's what's going on. And in my opinion, it's kind of fine. I've seen a lot of games literally do not give a shit about that. You can tweak your like near clipping plane to kind of resolve that, but I mean, a lot of shooters, for example, don't give a shit. So there's a fisheye effect in shooters. Have you noticed that? So yeah, so maybe it's fine. Maybe I can do something about it, but I don't know. It's too much effort, in my opinion. It's too much effort. So, and this is not that big of a problem. The real problem begins, what if the point is located right at your eye? So that's the most interesting thing. What is it? It's right at your eye. So if it's right at your eye, its z is equal to 0. So enumerate with Lebits. It's great to see you going back to the software rendering. Very nostalgic for the Olive C streams. Building my own hardware render for the Dreamcast right now. Nice. So it's always cool to see you doing more graphic stuff. Yeah, I kind of enjoy this topic, right? So it's kind of a cool topic because this is something that I was obsessed about when I only started programming, right? So because I started programming because I was doing a lot of like, Warcraft 3 maps. So I came to programming from gaming, right? So I came programming from gaming, and because of that, I naturally kind of was like looking for the ways, how do I make my own game, right? So, and I was obsessed about 3D and stuff like that, and I learned a lot of these formulas when I was young. So yeah, it's kind of nice for me to go back to all of this. I really like that. Very nostalgic for me as well. Very nostalgic for me as well. So, okay, you can kind of maybe ignore this kind of stuff, and especially what's going to happen if you have a point which is, I don't know, like behind F5. So at this point, if you are projecting, right, if you try to project it, right, so look, I'm projecting, it's actually inverting. It is effectively inverting. So it's on that side, right? It's on that side, and it already inverts itself onto the screen. So if you go behind, it's actually upside down. And in fact, as far as I know, the way our eye works is that it projects the image on its retina upside down, and there was some sort of a mechanism to sort of invert that or something. Do you guys know what I'm talking about? Right, so yeah, because the light crosses our eye, right? And then because it goes behind, it just like goes upside down. This is literally the same effect. This is literally the same effect. So it just goes upside down. So, and it's definitely, you have to do something about that, right? You definitely have to do something about that. But the real problem begins when you have a triangle that one part of the triangle is behind your eye and another part of the triangle is behind the screen. How the fuck do you even deal with all of that? That's the funniest part. This is all of the shit that I had pleasure to discover when I was actually writing a game with my silly rasterizer, right? So it's just like, you know, for demoing things, it's kind of easy to slap together x divided by z, y divided by z. But when it comes to a real software development, real game development, like, well, you probably have to do more than that, right? So what's going to happen if that's the situation, right? So a lot of corny cases, as you can see, a lot of corny cases. So this is the I. This is le Z, and this is X. So, and this is le screen. And imagine you have, this is P1, right? This is P2, right? This is P2, and this is P3. And this is only one slice of the 3D space. They can be also skewed along the other axis, right? So, and this is the thing that we need to render somehow. This is the thing that we need to render somehow. So the way the rasterizer works, at least the one that I'm making, it rasterizes only triangles, right? So because the triangle is a very nice primitive, right? So it's a classical thing to rasterize with triangles. So like they're easy to work with. They're extremely easy to work with. So, and essentially the way you do that, you only project on the screen the vertices of the triangle, right? So that means I'm going to be projecting this thing. So this is P2 projected. This is P3, it goes here, P3 projected. So we have two things that are successfully projected in here. And now this thing. If we want to clip this thing and we're going to say, okay, we're going to ignore it. Well, we don't have a third vertex to render on a screen. So that means we don't render this triangle at all, but part of the triangle is visible. We have to render something. That's the thing. In case of far clipping plane, it is super easy, right? So if you have a triangle that kind of crosses the far clipping plane halfway through, you project all three of them, start rasterizing the pixels of the triangles, but since you keep track of the z value of each individual pixel of the triangle, you can just ignore the pixels that are far plane. But here, you can't even properly project this motherfucker, because if you try to project it, it's going to be upside down. So this particular thing, instead of being somewhere here, it's going to be somewhere here. Like, what the fuck do you even do? Exactly. So far clipping plane is very easy, but the near clipping plane is a huge pain in the ass, and this is literally, you have to modify the mesh. You literally have to modify the fucking mesh. So, and as far as I can tell, you can have like several cases in here, right? So you can have several cases. So let's actually see what kind of cases can we have in here. So let's go with something like this. So this is the eye, right? So this is the eye, and this is le screen. I should stop saying it like that. I'm really sorry. So, and we can actually put the near clipping plane at the 0. But again, if we put it at the 0, we'll have to deal with the case when z is equal to 0, and that's division by 0. So usually near clipping plane can be put somewhere, I don't know, here, right? We can even project on the near clipping plane to get rid of the, what is it called, of the fisheye effect. But honestly, the clipping plane of the size 1 is actually too far away. You're going to be clipping like a lot of things. You're going to be clipping a lot of things. Like you're just approaching the object, and object already starts disappearing, starts having holes, right? Because of that, at least for my case, I'm going to put near clipping plane in here, but the projection somewhere here. Though I can move projection to here. I don't know, it's just like, so what's important in here is that these two things are kind of separate, and you can vary them, where you project and where you actually clip. right? So you can vary them. So in the first case is very simple. It's just like there's no clipping at all, right? So this is a very simple case. And I suppose nothing needs to be done. Nothing needs to be done. Though, how do you check that a particular point is crossed the clipping plane? I suppose you can just check its z-value. If it's z-value less than the z-value of the near clipping plane, that means it is behind the near clipping plane. You have to do something with this. But anyway, so this is the first case. This is the first case. The second case is going to be when one vertex cross the near clipping plane. Right, so this is one case in here. The question is, what do you do in this specific case? So this is near, this is screen. One point picked in here, and we have to eliminate it. Right, okay, so can I always have to switch to this. Is there any shortcut to switch? Yeah, there is no shortcut for that. Oh, okay, so it works now. So there is a shortcut to like do a straight line, and it worked on shift. At some point it stopped working, and now it is working again. I have no idea what happened. Maybe I updated my software, but whatever. So what do we do in this specific case? Right, so instead of triangle, we don't have a triangle anymore. Notice, by the way, notice. Oh, fuck. This is not because of shift, it's because I switched. I'm an idiot. Whatever. Right, so instead of triangle, what we have is this. I don't even know how to call this. This is a polygon. So what we have to do in this specific case is probably split it into two triangles and render two separate triangles. But luckily, these two separate triangles are already in front of the clipping plane, so you don't really have to do anything about them, right? So as soon as one vertex crosses the near clipping plane, the triangle splits in two. So this is the kind of shit we deal with. So Blender calls them n-gons, 3ds Max polygons. But in reality, it depends on how your rasterizer works. They can just split all of these polygons into the triangles anyway. Because my paint is written in Python. I don't think it's because of that, right? It's because something is broken here. So when it worked, it was still written in Python. Then it stopped working and it's still written in Python. So I came to a conclusion that whether the shift working or not working has nothing to do with Python, because in both of the cases it was still written in Python. So you know what I'm saying? It's just like, I think it's an irrelevant variable in this experiment. Anyways, so this is the second case, right? So this is the second case. Right, so this is another one. Let's fucking go. And this is... So now you have 2 points crossing the near clipping plane, right? So that's the second case. That's the second case. This one is rather easy case because you just render one triangle but smaller. So the only thing you need to do, by the way, is to project these points in here. But it's rather easy. We already know how to project things like from the world to the eye. Here we can just consider that as sort of a vector and use the same similar triangle formula to project this, like find this specific intersection in here. We already can do that, so it's not that big of a deal in my opinion. It's not that big of a deal. Right, and the same thing in here, I suppose. The same thing in here. So we just have to create like a single triangle. So in here, might as well maybe even put stuff like that. All right, so that's what we have in here. 2 triangles. All right, so let me indicate that it's 2 of them. Okay, and the last case is actually kind of obvious. It's like all of them are behind the clipping plane. Right, so the entire triangle is behind the clipping plane. What do we do in this case? This is the most difficult case, by the way. What do we do in this case? I guess nothing. We just don't render it, right? So we just like ignore it. So yeah. So I suppose to implement the near clipping plane for our specific case, we just have to consider these 3 cases, right? And it's really not that many cases, honestly. It's not that many cases, right? And it doesn't really matter which vertex, which one vertex to cross. It's always going to be 2 triangles. It just doesn't matter. If you mentally like rotate this triangle and make sure only one vertex crosses, it's always 2 of them. It's always this like, you know, a polygon of 4 things. Quadragon. I don't know how to call it. I'm not familiar with the English terminology. So yeah, how does our rasterizer works? Quadragon, quadrilateral, yeah, quadrilateral. Let's freaking take a look, Barabskis. Let's freaking take a look. Where is my game? So I think I have a renderer. Yeah, so I did a little bit of a refactoring and stuff like that and changed things around and so on and so forth. So we have a structure. By the way, did you know that in C you have anonymous structures? Right, so you can do that. You can basically define a structure and then immediately define a variable of the type of that structure, right? And then you can initialize this kind of things. Since I didn't really plan to pass this type around anywhere because it's a global variable, I didn't feel the need to actually define it as a separate type. So you can do this kind of stuff, by the way, in C. I don't know if it's like a maybe some later standards, but it kind of works and it's kind of convenient, right? So for this like one-off structures. Right, so and in here we have 2 dynamic arrays. I'm known as the dynamic array guy, right? So obviously I'm using dynamic arrays in here for my renderer. So here is the dynamic array of vector 3s, and vector 3 is XYZ, right? So you probably know what is a vector 3. Right, and then you have colors, and the colors is a dynamic array of colors, right? So that's what it is. And these are 2 parallel arrays. So that means they always have to have the same size, and each parallel element is actually related to each other. So essentially what we have in here is vertices, right? So vertices of the triangle, right? So you have V1, V2, V3, V4, V5, V6, and then continues in here. Then you have colors. And this is going to be C1, C2, C3, C4, C5, C6, and then it continues in here. Right, and obviously what this color means, it's the color of this specific vertex. And they're just flat like that. And what they represent a sequence of triangles, right? So this is the first triangle. So then goes the second triangle, and so on and so forth. So it's kind of difficult, it's kind of similar to the buffers in OpenGL, right? So you can have like a vertex buffer or something like that. So this is the buffers. We put data into those buffers, and then we have a function that takes that data and tries to rasterize that. C3 mentioned. Okay, anyway, so we have a function renderer push vertex, renderer push vertex. What it does, it takes a vertex and its corresponding color and just pushes it in here. So the way you render a triangle, for example, I want to render this floor triangle in here. How do I do that? I just perform 3 pushes. So where is the thing? Yeah, there you go. So here is me adding the rainbow triangle. So I do push, I create basically the vertices for each individual vertex of the triangle, and then as you can see I'm setting a color red, green and blue, separate colors on each individual vertex, and this is how you render a single triangle. Right, so if I need to render a Utah teapot, here I just created a separate function, I'm iterating the faces of the mesh of Utah teapot, right? So I literally have a hard-coded array. So here is the vertices of the Utah teapot. There is 3,646 vertices for this specific teapot, and there's 6,320 faces, right? So I'm just literally iterating the entire mesh, and as I'm iterating the entire mesh, I just pushing the vertices into the renderer. So every time you want to render something, you just push the vertices into this renderer, and then there is a function called renderer flush. So if you take a look at it, it's straight up code from Olive-C. So that code that we ripped off from Olive-C, it iterates the vertices of the renderer, and just renders the triangles, right? So the usual way, using the barycentric coordinates and then interpolation of the colors and so on and so forth. There's a little bit of a fog and stuff like that. So that's the whole architecture, current architecture of the rasterizer. Pretty cool, right? So it's just like, it's very simple. It's also very slow, but it's also pretty simple. It's just like it's two arrays. You just push vertices and then you just like rasterize them. So, and I also have a function render reset, which resets both of the arrays to 0, cleans up some of the buffers and stuff like that. And now we even have an immediate API in here where I have render reset. Maybe I should have called it render begin. Then I push vertices and then render flush. So maybe it makes sense to literally rename this kind of stuff to render begin. Look at that. And then take render flush, call it render end. I'm going to replace render end. And I just re-implemented OpenGL 1.0. Do you know how like OpenGL 1.0 actually works? You have GL begin, GL end, right? So GL triangle, GL vertex and stuff like that. That's literally that. So it's basically GL begin. I can literally rename render begin to GL begin, and everybody would think that I'm using OpenGL, but in reality I don't. I don't use OpenGL, but everyone thinks I'm using OpenGL. I'm sorry. I just want to give a shout out to Triangle Strips. Had to learn how to make Triangle Strip converted to make PS2 compatible models for modding projects I've been working on. Yeah, that's classic. That's freaking classic. So I don't know. We don't use the Triangle Strips, but maybe we will. I don't know. Maybe we'll also can implement this mode where we have for you the teapot, where you have a buffer of vertices and then you have a buffer of faces, so sort of like a level of indirection. But I'm not really sure how that level of indirection will affect software render, because I feel like on CPU that just means that you're going to be jumping around the vertex buffer, and that is kind of bad for the cache. Look at this thing. Right, literally, if you have this indirection where you have buffer of vertices and buffer of faces, you iterate the buffer of faces to render things, you literally jump in between the vertices and it's just like all over the place. You're missing the cache all the time, and I feel like it's going to be slow. So what you probably want to do instead is have like a continuous array of triangles that you just continuously iterate and render, don't you? I think that's what you want to do. Right, but I don't know. We'll see. So all of that needs to be studied, all of that needs to be measured. It's just like hypothesis, right? So we don't have a specific number. Sounds logical. Yeah, sounds logical. But with the performance, you kind of never know, right? So you have one hypothesis, you test the hypothesis, and it turns out wrong, right? So just like you need to measure. But not right now. Or to measure something, you need to have something that is working. And as of right now, we have shit that is not particularly working. Like, what's the point of measuring something that doesn't fucking work, right? So let's focus on making it work. And then we can try to measure the performance of something that actually works, right? So that would be great, I think. That would be great. So anyways, so I suppose we have to do this particular clipping at the time when we push the vertex, right? I think that's what we have to do. But look, we are pushing each individual vertices independent from each other. But here, to actually perform the clipping, we kind of need to know all of the three vertices at once. We need to know all of the three vertices at once. And because of that, I think this abstraction that just push vertex is not going to cut it, in my opinion. I think it's not going to cut it. So what we have to introduce in here is probably, so render push triangle. Right, so this is going to push triangle, and this thing is probably going to be implemented in terms of push vertex, and it's going to push only the vertices that are needed. In fact, in the case 2, Electric Boogaloo, you're actually going to push 6 vertices. Right, so yeah, there should be some sort of like abstraction on top in here, that's for sure. All right, let's start coding already. Right, so we're going to have A, B, and C. Right, so let's call it V1, Zulu, V2, vector 3, V3, right? So this is what we got. And then we're going to have a color C1, color C2, color C3. There you go. So what are we doing? I think we need to, yeah. we need to know whether the vertex is behind the near clipping plane or after the near clipping plane. So as of right now, the far and near clipping plane are just variables in here. I think the first thing we need to do is to put them into the constants and make them global and available for everyone. Let's call them maybe near, right? So, what the fuck is going on? What? Okay. So, I forgot how to use Emacs. I don't know what the fuck is going on. Near clip, and this is the far clip. So this is basically equals. We don't really care about that. So let me quickly go to the compilation errors. Just a second. Through the compilation errors. Okay, so this one is not implemented yet. So far clip and next error. It doesn't show the next error. That's really weird. So near clip. All right. Triangle. Okay, so in here, we're gonna assume that you're pushing already things that are transformed and positioned right in front of the camera. So the way it all works, by the way, is that when you're moving around or rotating, we don't rotate right now, right? I didn't spend time doing that, but we're moving around. So we're not really moving the camera. In fact, the camera is always positioned at the origin 0, 0, 0. What we're doing, we're moving the world because that's easier. So the math of projecting things on the camera when the camera is positioned at 0, 0, 0 and looking forward along the z-axis is extremely simple. I already mentioned that math. It's x over z. As soon as you mathematically move the camera somewhere else, the projection becomes very difficult, right? So you start to have a lot of different cases and stuff like that. So instead of that, instead of moving the camera, what usually people do, they move the entire world. Right, because it works, right? So it's just like, and it keeps the math simple, right? So you can still use this formula of x divided by z without like moving anything, right? And you also have the camera. So when you rotate the camera, in reality, you don't really rotate the camera, you rotate also the whole world, right? So the whole world around the camera is just like doing different things just to keep the math simple. And it makes sense, right? So it's a theory of relativity. Who cares whether it's the actually camera moving or it's the world moving around the camera? For the observer, it doesn't make any fucking difference, right? So for the observer, it doesn't make any freaking difference. So the 3D games have always worked like a spaceship in Futurama. Exactly, they always work like that, like the spaceship. So it just moves the entire world around the camera. Yes. But anyway. And we're going to assume that the vertices that you're pushing are already transformed, right? So you already did all of the transformation, moved it, and positioned it in front of the camera, right? So, and if we take a look at how we position Utah teapot, where is the function? Here it is. So we grab the face, we construct the vertex from that face, and as you can see, we also rotate it. Right, so we also rotate it. We keep track of the Utah teapot angle. As you can see, Utah teapot is rotating. It's just a separate variable. And only then we're pushing in it. So that's the convention of our rasterizer. It assumes that the vertices already are positioned. When quaternions, a little bit in the future, we'll get to the quaternions. I also want to take a look at this idea of not using quaternions and using rollers instead. Right, so because there is this discourse, right, whether quaternions are a good way to think about rotation, right? So maybe there's a different way to think about rotation. Using what? Well, let me actually find that. So I'm gonna copy paste this thing, open the browser. Quaternions versus rotors. I think it's rotors versus quaternions. So there is this very interesting discourse that quaternions are not the great way to think about this kind of stuff. And you should think about these rotations differently. I think that's the main article that everyone refers to. I think that that's the main article. I don't know anything about rotors. I just heard about them. And it's just like at the back of my head. And I want to spend some time just reading this article. Right, maybe we can read it together at some point and then just see if I can apply this idea in my game, right? Because quaternions, they're kind of mathy, they're kind of nerdy, right? So, and everyone treats them like a black box. Everyone just treats them like a black box there where they feed the angles and they get back rotated thing, and it's just like nobody fucking understands how they work internally. And I hate that. I absolutely hate black boxes, because what if that black box breaks? What if that black box breaks? I need to go inside of it, understand what's going on, but I can't go inside of the black box, right? Don't fucking understand it. So if there is an abstraction that is basically isomorphic to quaternions, but it's easy to understand, I'll take that any day. I'll take that any day, because that means I can modify it, right? Maybe extend it, right? So do something else with it. So, and yeah, I need to spend some time to actually learn this kind of thing. So I'm going to put that in the description, by the way. I think it's a good idea to put that in the description. Description. Sounds like a great stream idea. I should have actually went into software rendering back a long time ago. There's a lot of content in here as far as I can see. So anyways, so what are we doing? Let's go back to the code. So here's the rotations and stuff like that. So since we established that all of that stuff is already pre-rotated and pre-translated for us, one of the ways to check whether, for example, this thing is behind the clipping plane is basically whether it's less than near clip. Right, so it's already in front of us, so we can just try to check that. So, and we need to distinguish different cases in here. So maybe we can have a counter, right? So that does something like this. So it's a V1, V2, V3, right? And there you go. You can just switch upon different cases in here. So case 0, 0 of them are behind the clipping plane. So you literally push all of them into the thing, right? So V2, C2, V3, C3. There you go. So another one, case 1, it's when only one, but now you have 3 cases. Is that a V1 or is that a V2? Is that a V3? Which one exactly? Which one exactly? So this is not a particularly convenient abstraction. So what I'm thinking is that, what if we actually keep track of these specific things too? For example, okay, this is C, and so C stands for clipped, right? So maybe clipped, and there is a 3 of them, and this is initially 0, obviously, and this is more like a clipped count, right? Clipped count. And essentially, if this one is clipped, what I have to do, I have a mini dynamic array in here, mini dynamic array, right? So I just do ++, and I push this thing in here. And I can repeat the whole thing for each individual thing in here. So this is going to be that, this is going to be that, so this is V2, V3. And so now clipped count acts like a count how many of them are clipped. And on top of that, I know exactly which one, because it's going to be essentially clipped 0, right? So clipped 0. So this is rather convenient. So it's a counter, and this is a mini dynamic array with a fixed size. And since it's allocated on the stack, I don't have to think about deallocating it, right? So it's totally fine in here, I think. So if it's that one, right, if that's one, now I need to take the 2 ones that are unclipped. But the unclipped, which one are unclipped? Maybe we need to have 2 dynamic arrays? Is that a good idea even? I'm not really sure. Dynamic arrays with a fixed size, my favorite. Well, I mean, fixed capacity. Got you. It's not a fixed size, it's fixed capacity, right? So the size is count, the size of count, but the capacity is 3. See, that's the difference, So this is an unclipped count, okay. So, and essentially here, we can just do the following thing, right? So if it's unclipped, right? So if it's unclipped, you just literally do unclipped. So there you go. So for all of them, a boom. Boom. But probably not like that. Probably more like this. Can I do something cursed, chat? Can I do something absolutely fucking cursed? For instance, what if this is the condition? And in here, I actually return this, but as a, I feel like I'm gonna stumble upon like an undefined behavior. But just a second, chat. I want to try that. Okay, so then I dereference this entire thing and assign v1 to that. What do you guys think? This versus this. It's chat. It's shorter. Given the same amount of names, it is shorter. So, that's disgusting. I know you would like it. I know you would like it. But anyway, okay. So fine. I'm gonna keep it like that. Right, so now we can distinguish whether something clipped or something is unclipped, and so on and so forth. And so on and so forth. So I don't really like how long these names are. You know what I mean? So what if I maybe rename the whole thing to C, right? So this is C, and C count is, you know, CC. Is that a good idea? I feel like it's going to be too cryptic. Right. I'm going to try to rename them once I'm done writing the code. Okay, so essentially, this is the vertex that is clipped, and these are the vertices that are unclipped. There you go. You know exactly now. This is actually a cool approach. Look at that. It's kind of a cool approach. So you know exactly which one is clipped and which one are the opposite ones. And it doesn't matter, like any of them can become that, and yeah, this just collapses all of the 3 cases in here just by doing this kind of stuff. Damn, I like it. Actually, I like it. But anyways, so what do we need to do? We need to understand how to project all of that stuff. So I probably need to do something like this. So this is the origins. And you effectively have like some sort of like a z value, right? So let's call it like a screen, not really screen value, but well, let's call it near, right? Because it's like literally the value we're working with. And you have 1 point, P1, P2, and you need to find the PC. You need to find PC. Which is clipped, right? So this is basically clipped. So this is going to be something like that, right? So, and this one is something like this. How exactly do you find this stuff, right? So this is Z and this is X. Well, PC, XC is unknown, right? That specific XC is unknown, but the Z value of PC is known. It's literally the near clipping plane, literally, because it literally stands on the near clipping plane. The only thing we need to find in here, is XC. So we can use a similar triangles, right? So similar triangle situation. So this is the triangle. So this is the first triangle, the bigger triangle, right? The bigger triangle, and this is the smaller triangle. So they're similar. They're literally similar. So what we can do, we can say that the XZ value, which is near, right? So the near minus the Z value of P1, Z1, over the X value, which is XC, minus X1, is this relationship is literally the same as this one, the relationship between these 2 points, which is Z2 minus Z1, right, and X2 minus X1. There you go. Everything is known in here. This value is known, this known, this value is known, this value is known, all of that is known except of XC. What you have to do now is just like rearrange everything so you know XC. Why are you doing math? Because I'm doing software development. Software development is a form of math. Need to calculate the code too. That's a good point. Thank you for pointing it out. Okay, so let's actually think about it. So on top of, I completely forgot. You see how fucked up near clipping plane is. Far clipping plane, easy. You have a Z buffer, you already automatically have that. Near clipping plane, oh god. God save us all. Okay, so essentially you probably have also callers C1 and C2, and you need to find CC, 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 EPC, CC, and PC. Right. So well, essentially, since this point stands. Lays on this particular side, that is just a linear interpolation, I suppose. That's just a linear interpolation. So, and that way you will have CC and PC. So yeah, I think that's what we're gonna. But we're not gonna be doing it right now. We're not gonna be doing it right now. A little bit later. So for now, we need to rearrange this stuff. And find XC. All right, so I suppose we probably need to move this entire thing to here, right? We need to move this entire thing into here and move this entire thing to here, right? That's what we need to do. As we move this entire thing to the right, it's not going to be reciprocal anymore. It's going to be a normal thing. But this thing, it has to be put upside down. Do you guys understand what the fuck am I talking about? Do you guys understand? Anyway, so xc minus x1, right? Right, is going to be equal to x2, x1 divided by z2, z1, right? So this is that, but upside down, and then multiplied by the near minus z1, right? And since we need to find xc, now we have to move this thing to here, and it's going to become positive since it was negative, right? So it's going to be, can I just, I don't want to write it down, like again, can I just do something like plus x1, plus x1, thank you very much. This makes sense? What do you think? Did you see any errors in here? So this is xc. So does it make sense? I think it does. So, and we know all of the stuff in here, right? So it looks fine. And we need to do the same shit for y, right? So if we, because it's in 3D and stuff like that, so it has to be like yc, and literally the same, just replace x with y. Just replace x with y. Finally, what if the, yeah, this one is interesting. So you can have a division by 0 in here, but you're only going to have a division by 0 if they're literally the same. So yeah. So I think they can be equal to 0, but what's going to happen in that case? So, so in case of a triangle, so let's see. This is a very bad it's a line. It's a motherfucking line. This is the triangle, which is going to be like, right? Yeah, so when they're not a triangle. I guess we can just ignore this kind of case, and if it occurs, probably some sort of a glitch will happen, and if it happens, we'll put some sort of a hack in there. You know, so I think this is how I'm gonna go. Plus 0, well, we can put some plus 0, 1, but for now I'm gonna just ignore it. Wait for a glitch occurring, and then if glitch occurs, like I'll have a node, right, so that this is something that we ignore, and then it's just gonna, so if it's equal to 0, just discard the entire, this is something that we can do right now, by the way. So if this is such a bad triangle, just fucking discard it. What's the point of rendering then? Yeah, also assert. Assert is a good idea, by the way. Assert is a good idea. Thank you so much. I think we even have something like epsilon somewhere. I think it's in the vectors. So yeah. So I usually compare by that specific epsilon, right? And we can just do something like that. Anyways. Excuse me. All right, so do we have some sort of a le projezione? Can I split my screen just to have this formula somewhere? Yeah. So we need to create 2 points effectively. How are we going to call these points? Maybe since we usually call points P, let's call them maybe Q, Q1 and Q2. Q1 and Q2. That's a good name for them. So the first one is going to be Q1. So vector Q1. And in here we're going to put something like that. So in terms of Z, it's going to be the near clip, right? That's the Z value of Q1, and this is Q2. I'm going to put it somewhere here. So the interesting thing starts with X, right? So the interesting thing starts with X. Where is the formula? So X2 minus X1, and interestingly, so this is X1, that means the X1 is clipped one. Okay, so I'm gonna just put it like that. So this, all of that stuff below, it doesn't matter, it's just like a scratch place. Unclipped 0 X minus clipped 0 X. Okay, so this is more like a dx. This is more like a dx, but I'm not really sure if it's a good idea to keep it like that, but whatever. So then we divide by literally the same thing, but z, right? So this is going to be z, like so. Yeah, so that, what the fuck did I just do? So it's x, this one is z. I kind of want to factor them out. So this is going to be dx, so float dx. And this is going to be dz, float dz, dz. So then we multiply by near clipping plane minus z1, which is this thing, right? Minus z1, which is minus this thing, and we add x1, x1, which is this thing. Yeah, I think that's basically what we have in here. That's basically. Now we have to do the same thing for y, which means that we need to have dy, right? So this is dy, dy. This one is dy, and this is just y, right? So that's the first x we have in here. That's the first x. And we have to repeat the same thing for unclipped but 1. Right. Did I make any mistakes? I think I didn't make any mistakes, right? So this is the, yeah, this one. Okay, so that's totally fine. All right, so the second one starts somewhere here. So unclipped 1, this is unclipped 1, but this one is 2. So we've got x1, q1 and q2. Here they are. But there's a lot of a duplicate code in here, which means that I probably want to factor it out. I want to factor it out somehow. So let's quickly do that. Maybe static inline. Maybe, like, I don't really know how to call that. Effectively, what we have is 2 points, vector 3a, vector 3, we can call p1 and p2, right? So, and some sort of like a z, right? So it's a z-plane. It's called z-plane. Maybe like this. So in this one, does it return anything? It should return vector 3. Vector 3. All right, so, and let me put this stuff in here. So v1 is a clipped one, I guarantee you. v1, well, fuck. Let's start with unclipped one then. Unclipped one is p2. This one is p1. Near clip is z-plane. Right. Is z-plane a good name? If we just called it z, I think it would be fine. Yeah. Yeah, that's a good one. And then we can just return q1. And because it's such a simple code, right, we can just call it Q. Okay, so that's good. That's good. So that means here Q1 is actually foo. Do you guys have any idea how to call it? Clip line. Yeah, clip line. Clip line. So that's a good one. Thank you so much. So now I can say clipped 0, and this is unclipped 0. Clip 0. So there is a little bit of a condition that they have to be on the opposite side of near clip, but we're gonna just assume that you know that before using this function. So, and all of that can be removed easily. So it's a Q2, and this is unclipped 1. And by the way, we can reuse that function for the case 2 as well, because we literally will have to do the same thing in here. All right. So it's actually kind of a useful function. This is insanely useful function, I think. Assert inside, you know, asserting on each individual thing is just kind of a too much in terms of performance, right? So I kind of don't want to do that. But I mean, I know that asserts are disableable, but I don't feel like doing it right now. Anyways, so now we have to construct 3 triangles, right? So that's what we have to do. So this one is a P1, right? So this is a P1. And obviously, one triangle is going to be this one unclipped and both of these two. Both of these two. Nah, no, not really. So P1, P2, P3. Okay, so 1 and 2 clipped. So that's first triangle. So renderer, push vertex, unclipped 0. Q1, Q2. So that's the first vertex. I kind of want to, yeah, so we have to push them separately, that's true. So Q1, Q2, and we also have to put the colors, but I'm not really sure what colors to put in there. So I'm gonna just put the first one, so because we need to interpolate them. We need to interpolate them. One. Or maybe, can I just put purple in there? Purple. So then I know what needs to be fixed. All right, so this is the first one. This one unclipped and 2 of this. Then second, but which one? Yeah, this one is interesting. You have to be a little bit careful. So this one, yeah, I feel like, so the first clipped is always, Q1 is always the projection of unclipped. Q1 is always the projection of unclipped. Unclipped 0 specifically. So that means this second triangle is going to be these two, but the second Q, I think it is persistent like that. So that means I can do 0, 1, and the second, because the first one is always the projection of unclipped 0. So that means the second one is always the projection of the unclipped 1. So that's how you form the 3 triangles in here. There we go. I think we formed it. Chad, is he using barycentric rasterization? Yes, it's a barycentric rasterization. So that's the barycentric. Barycentric. Okay, so now we have the case 2, electric boogaloo. So what are we doing here is that, so this is also kind of Q1 and Q2, but now the triangle is only going to be 1. And I think since we have this tool to actually project things, I think it's super easy. So we need to clip line. So now you have 2 clipped and 1 unclipped, right? So this is a clipped 0 and unclipped 0. In the near clipping pane, this is the 1. Then clipped 1 and unclipped 0. So here is the Q1 and Q2. And the triangle that you form out of that is Q1, so that's the first one, so it's going to be purple, Q2, and unclipped 0, the only unclipped in here. So that's a very easy case, since we already have a function for clipping this kind of stuff, so it's no-brainer, in my opinion. Literally no-brainer. Now it's 3. All of them are clipped. Nothing. Might as well put a default in here. It's just like, yeah. Maybe somewhere here even. So not that much, honestly, not that much. And we don't really do any allocations. It's all on the stack. I suppose maybe the compiler will be also able to optimize all of that, hopefully. Right, so I don't know. Make case 2 not purple. Maybe we can make it. So what should it be then? Green. Something like green. That's a good one. Okay, so let's try to compile this and test stuff and see how it's going to work. So semicolons. Spend 3 hours debugging and it was a single missing semicolon. Alright, so what's wrong in here? So renderer push C1. Well, yeah. So freaking idiot. So this has to be vertex. Vertex. Okay, this one. Renderer. I think I need to make a small break, chat. I think I need to make a small break. Purple, finally. So do we have red? I don't even have a colors in here. Huh, that's very interesting. I do have background. Yeah, so here's the background and stuff like that. So maybe we can easily do something like red. Basically reinventing our own Raylib. I'm really sorry, Raysan. I'm reinventing Raylib from scratch with software rendering. By the way, Raysan on Twitter said that Raylib is going to support like software rendering at some point, or it's already supporting. Right, so we could just use Raylib. But I mean, I want to make it everything myself. I want to see the face of Raysan when I release the game and he's about to retweet it and say, "Look what you can do with Raylib," and I this doesn't use Raylib. Raylib is great, by the way. Raylib is great. Go use Raylib. It's a very cool library. But I just want to try to make it myself. Raylib will render Olive-C. Well, honestly, Olive-C is not really production-ready library, so I'm not sure if anybody would render it. Speaking of, by the way, do I have blue sky? Where is the blue sky? I want to find some stuff. Just a sec. Oh, it logged me out. Fuck. It logged me out. But somebody actually posted at me a very cool thing. A very cool thing. So, just a sec. Yeah, so this is the post essentially, right? This is the post. So I cheated a bit with the 3D render. So what they're making is, I don't really know what they're making. I feel like, yeah, so this is some sort of like a home project device on a breadboard and stuff like that. And they made a 3D renderer. It's a little bit too loud. It's a little bit too loud. Let me make it. And they used Olive-C to render this 3D thing. This is with Olive-C, apparently. At least the creator claims so. I didn't know you... That's really cool. Because the Olive-C project has tools to basically convert OBJ files into C code and basically make any kind of like similar demo that we have in here. Right, so I suppose this is what they use, and it can even work with textures. So there is a little bit of a textures in here as far as I can tell. I think this is textures. Right, so yeah. Apparently people use this library. I didn't know that, right? So, it's not particularly production ready, but people use it for things. So yeah, that's pretty cool. By the way, so I need to maybe put this link to the description for people on YouTube. Yeah, so that's basically the thing. It's kind of cool. It's kind of cool. Production ready is a big lie. Well, I mean, whatever is already used in production successfully is production ready. So it's kind of it's more of a marketing term, right? So it's more of a marketing term. But anyways, so red color is 255 and A is 255. So that's what it is. So green, it's basically a G. Can I align this kind of stuff? And this is gonna be blue. I just want to define a bunch of colors, you know? Just define a bunch of colors. And we definitely need to have purple. Does anybody remember what is purple? I think it's a red plus blue. I'm sure it is red plus blue. So, yeah, that's it for now. I think that's it for now. Okay, so label at the end of the compound. I think... yeah, that's kind of stupid that it requires you to have this additional thing, right? So you can't have an empty default body unless you like put this thing. So might as well maybe put it like that. Right. This is magenta. I don't know. Sure, I don't speak English. Enumerate, thank you so much. I forgot to mention it before, but someone started the repo on GitHub, which reminded me of it. Another cool 3D rendering library called Plush by Justin Frankel of Nullsoft. Oh, I think I heard about them. The Winamp guys. Pretty sure also software rendered back from the DOS days. That's nice. That's actually super cool. Labels needs to be followed by the statements. Empty statements also works. I think it's a syntax that comes from B. I feel like it's a syntax that comes from B. B had a lot of cases where you have something and it always have to follow by the statement. Always. It's just kind of a weird syntax, but this is what Ken Thompson required you to do, and Dennis Ritchie. So, anyways, B is not my programming language. I only made a compiler for it. Okay, so now we should start using the triangles, right? So we should not use push vertex anymore. Maybe it should also be called clipped. I think it's kind of important to call it clipped to sort of emphasize that it is in fact clipped. So push Utah teapot. Okay, so and when I'm, yeah, we also push like the colors for each individual vertex. Renderer push vertex, and the vertex that we're pushing is v1, v2, v3, and let's put this stuff 3 times. There we go. So, and the last thing we do in here is this renderer push triangle. Push triangle? Wait, what? Renderer. I made that mistake yet again. Push triangle clipped, and these are the things. Can I just more conveniently do that? Is it possible for me to maybe copy paste this kind of stuff using a little bit of an Emacs magic, like so? Then in here, 1, 2, 3. So this is the colors. This is the colors, like so. And then just put that stuff in here, like so. See? Emacs magic. Emacs magic. Let's go. Let's fucking go. Alright, so this is gonna be 4. And let's remove that. So we're pushing the triangle. The triangle. With 3, so what you don't like. Push. Triangle clipped. Made a lot of stupid fucking mistakes, man. Too many stupid fucking... And it all compiles, shit. It all compiles. It all successfully compiles. Alright. Fuck. It's the other way around. Though I'm surprised that it kind of works. So if I go over it. Trippy peepee. Exactly. I think it works because we have, yeah. It's just, it's not a near clipping plane though. Graphics are hard, yeah, I agree with that actually. Near, how do we even use near clipping plane? How do we use the near clipping plane? Is that because, yeah, It's not a Utah anymore, yeah. It feels like the near clipping plane is just too far away. That's what it feels like. Is that what's going on? That's kind of weird. Because, yeah. Delta is better. I don't know what you guys are talking about. Should be a smaller value, but it's already kind of small. Should it be even smaller? Okay. I mean, let's make it even smaller. No, it feels like it stays the same. That's what it feels like. I think I know what's going on. I think I know what's going on because end render end. Fucking, we do transformation. I completely forgot about that. We do rotation before all of the stuff and everything, but transformation, we do that at the moment of rendering, which is kind of stupid, honestly. This is something that we have to do when we push the triangle. That's what we have to do. So here is the one subtraction. Here's another one. Yeah, so I think this is something that has to be done in here. And also this is correcting the aspect ratio. This one is actually kind of important thing, by the way. This is kind of important thing. If you don't do this aspect ratio correction, you get this shit. And this is literally the same thing that you get in the demos, right? So, and I didn't really care about the demos, so it's kind of stayed like that. Fat teapot. Yeah. So that's what's going on in here. And because of that, you have to do the aspect ratio correction. And aspect ratio is basically display height divided by display width. Who knows why you need to do that? Who knows why you need to do that? The reason why you have to do that is because we are not projecting 3D scene on the screen, right? So when I showed you this kind of stuff, right, so we have a 3D object and we're projecting it on a screen. This is actually not a screen. We're projecting it not on a screen. We're projecting it on an image with 0, 0 coordinate, with the origin at the center of the image. It is at the center of the image. Left edge is -1, right edge is -1, bottom is -1, and up is 1. I think I made a mistake somewhere. -1, 1, -1, 1. It's a normalized image. It's not a screen. It's a normalized image, and it's actually square. It is actually square. This is where we're projecting all that. But if we want to put that square image on the screen, we literally have to remap it on the screen. Screen is not square. It is rectangular. Because of that, we take this small square, a small normalized square, and we stretch it to the width of the screen. And because of that, the image looks stretched. What's the solution to that? What's the solution to that? The solution to that is when you render the 3D scene, you literally squish the whole 3D scene, the 3D coordinates of the scene, the mesh, squish it along the horizontal axis, squish it. And you squish it the same amount as the monitor is stretched. So then when you remap it onto the monitor, the whole scene is stretched, but since it's squished, it sort of normalizes. You know what I mean? This is basically what it is, right? So, and when you take height divided by width, you have basically a ratio how much you have to squish your entire scene, so when it's stretched back onto the screen, it looks normal. Right, so that's basically what it is. It's kind of a stupid solution, but I mean, it kind of works, right? So it makes it look normal. And because you have wider screen, you should be able to see more, right? And the wider the screen you have, the more we squish the scene. And the more we squish the scene, the more you can see. So it actually mathematically works. If you think about it, right, so this stupid hack mathematically is correct, right? So wider screen, you can see more. Wider screen, we squish the scene more, so you can see more. That's so fucking cool. Like, I really love this kind of shit. There's always a little bit of a proper math in any hack, right? So maybe there's no hack. Maybe hack is just a social construct. Hack is just a math that we do not deem beautiful, right? Hack is just a math that we do not deem beautiful. That's what it is. Anyways, so we have to do this kind. So do we do this shit also when pushing the things? This is a good question. This is a good question. Maybe we do, because we don't really have left and right clipping, right? So you have a near clipping plane and you have a far clipping plane, but there's also left and right because you have this sort of, how is it called, frustrum, right? So how do you pronounce that? Right, so there's a notion in 3D graphics, frustrum clipping. I forgot how to, yeah, frustrum clipping. Yeah. So, and it's basically has a left and also has a top and bottom trapezoid. Yeah, so 3D trapezoid essentially. When we're going to introduce that, how much we squish the scene also is going to affect what exactly we're clipping there. So because of that, I feel like this thing should be actually done in the clipping, like when we push the triangle. So this is where it should be done. And actually, it's actually super easy. I feel like it's super easy, right? So you push this thing in here, then you put this kind of stuff and then that kind of stuff. So because of that, you should probably never use push vertex. All right, so because it doesn't do necessary clipping. So it's kind of like an internal thing. But anyway, yeah. So push that, we apply this kind of stuff, then we figure out what's clipped, what's unclipped. And near clip, by the way, let me bring it back to 1/10, all right, just to see if it's affecting anything. And as aspect, okay, so let's actually make aspect a global value. I think it must be a global value. So this is the display, width and height, and define display aspect. And this is what we have in here. Let's fucking go. Okay, so this is gonna be a display. And boom. Boom, boom, boom. Let's go. And it doesn't like the fact that I forgot to remove the equals in here. Are you happy now? Okay. Okay, look at that. It is working. It is working. It is twerking. It is working, twerking, working. It's kind of slow, but I mean, yeah, that's fine. So, and this is literally the debug colors that we're using. Absolute trading, absolute budgeting, absolute budgeting. Okay, so let's go here. Something is fucked up with fog. I can clearly see that. Just a second. No, it's actually fine. All right. Okay. 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 Cool. So, like, we did that. We only need to interpolate the colors, I suppose. Damn, Brovsky. Damn. Cool. Absolutely fucking cool. Freaking this. FPS suffered, yeah. Well, I mean, you know, we have 6,000 triangles rendering. Right, so unoptimized rasterizer. Completely unoptimized. Just the dumbest solution ever. 6,000 triangles. Of course it is suffering. Just, you know, let me cook. Just let me cook. I only slapped it together recently on this week. Okay. So you want it to be faster? Okay, I'm gonna not push Utah teapot if that's what you want. Right, so I'm gonna remove the Utah teapot. Are you happy now? It's super fast now. It's absolutely perfect. Look at that. Look at that. Absolute budgeting. Kind of goes in a really weird, like, yeah, so I think it's fine. So at some point, like, I want to have like a floor, maybe with a checker pattern or something like that. So it's nice to have a Utah teapot as a sort of like a reference, right? So because just without the Utah teapot, this triangle looks weird, right? So because of the perspective, it kind of looks weird. But now it kind of looks fine, I think. This, what the fuck is this? Like, what the fuck is this in here? Something is fucked up with the z-axis because we're using z-axis to, right, to determine the fog. So, yeah, not quite sure, but yeah, we'll see. Color shift, maybe it's a color shift. So the way we compute the fog, right, so that's how we compute the fog. So we have, actually we don't have a z buffer. This is not a z buffer. It's a reciprocal of z buffer, right? So because this is something that you need for perspective correct interpolation, right? So that's what you have to do. So we turn it back into z, and then we just like do the blending and stuff like that. So there's something wrong with the reciprocal of z. Not 100% sure what the fuck is going on here. You're gonna try basic lighting? Yes, at some point. But we also need to do a little bit of a game development. It overflows. You think it overflows? Maybe it overflows. So, okay. It's a lot of closing braces. This is somebody who will never be able to code this shit. And by the way, you may say, oh, it's just an OpenGL or just a Unity, but this is completely from scratch, pixel by pixel in memory, Software Rasterizer. If you're focusing on small little braces in here, this tells me right away that you are noob and will never be able to code this. Just the truth, I'm sorry. And the only reason why I point out that braces is because you're seizing and coping, because you will never be able to do that. Sad but true. Exactly. Exactly. Toxic. Exactly. Software engineering is toxic. Because if it's not, you get the shit software of 2025. So you know why all of the software is shit today? Like literally everything is falling apart. Look at the YouTube, right? So YouTube interface is literally falling apart. And this is because they were trying to take out the toxicity from software engineering. So there's no pressure to write good software anymore. And when there's no pressure to write good software anymore, you get the modern YouTube. So enjoy your shit, YouTube. So I want to make a small break, by the way. I want to make a small break. I want to make a cup of tea. Yeah, after that, we're going to try to maybe do interpolation of some sort. Right. We are back. So we now need to fix the attributes, right? So when we're clipping the vertices, we also need to clip the attributes appropriately. So, but to clip the attributes, we need to do this interpolation. Where's the clipping? So here it is, right? So this is basically what we do. But we have to do interpolation in the 3D space, right? So we have to do interpolation on the vector. So let's consider the case when we just have interpolation in 1D space. Might as well actually put all of that into vec.h where I keep all of the math. All right, so we can have something like lerp. Right, so classical operation should be static inline, by the way, to let the compiler know that inline it aggressively as much as possible. So we have A and B, so float A, float B, and this is the interpolator. Interpolator is the value from 0 to 1, and if it's 0, the result has to be A, and if it's 1, the result has to be B. If it's something in between 0 and 1, it has to be something in between A and B. That's linear interpolation, if you didn't know. So that's how it works. It's a very simple concept, actually. It's an insanely simple concept. Once you wrap your head around linear interpolation, you can do pretty much anything. Like pretty much anything in computer graphics is some form of linear interpolation over something. So this mapping of like square on which we're projecting the 3D scene to the screen is literally linear interpolation. Everything is linear interpolation. And when you do this kind of linear interpolation, so you can take the distance between A and B, so like this, and you can interpolate that specific distance, right? So if it's going to be 0, the distance is going to be 0. If it's going to be 1, the distance is going to be full. But the distance is not really a value between A and B, so that means you have to shift it. So you have to add the A in here, and there you go. This is a linear interpolation over like one dimension, right? So That's what it is. Very simple thing, very simple concept. So on top of just a linear interpolation, there is also an inverse linear interpolation. This one is rather interesting. So you have a value A and B, and you have a value C, right? And this is a value not from 0 and 1. The value C is a value from A to B. And what this thing is supposed to return is a value from 0 to 1. So it's an inverse operation. If this thing returns a value from 0 to 1, based on A and B, this one returns a value A and from A to B based on this thing between A and B. Did I say it correctly? No. This one returns a value from A and B. This one returns the value from 0 to 1. So that's what it is. So this is another operation that we'll need in here. So how are we going to be doing all of that? So here is the A. C is somewhere here, B is somewhere here. So what we have to answer is like how much proportionally this segment is smaller than the whole segment in here, which means that we need to take the length of this segment and simply divide it by the length of the whole segment, which is B minus A. And I suppose this is the inverse slurp. Did I do that correctly? I think I did in fact do it correctly. So very simple operation, very simple operation. So now we have to do that in a 3D space and even in 2D space, right, 2D space. Linear interpolation in 2D space is, I suppose, rather simple, right? So you have vector A and vector B and float T, right? And what you effectively do, you just linearly interpolate each individual component of the vector. So you want to effectively lerp from AX to BX, and then from Y and Y, and you want to reconstruct back the vector out of that. The vector out of that, and that's your linear interpolation on this entire thing. So very simple. Very simple. So the inverse lerp for the 2D is kind of interesting, I suppose. So it is supposed to return float, and this is going to be vector. This one, by the way, should have called vector 2. Vector 2, electric boogaloo. So vector 2 ilerp. So it is accepting A and B, right? A and B, and also C, right? And it's supposed to return a value from 0 to 1. And there's kind of an assumption, there's a kind of an interesting assumption that C lies on a segment AB. It lies on a segment AB. So, and I suppose the way you do that, right, so you basically have the same situation with ilerp, right, so you have point in space A, then point in space B, they form a segment. So this is 1D, but think about it as 2D. You can think about it as 2D, right? So, and essentially you have C in here. So what you probably have to do, you have to take the length, of AC vector and then divide it by the length of AB vector. And there you go, you got the thing. So, but taking the length is kind of a, I don't know, kind of an expensive operation because it's a square root. It's kind of a square root. He can lerp without T. Yeah, I can. Well, I mean, the compiler will tell me that I made a mistake in here, so that's totally fine. I usually don't care about this kind of things. It's kind of the point of having statically typed language with compilation step. That's kind of the point. So anyway, so we can do something like vector 2 length, right? So let's call it len, and maybe we can call it distance, right? Distance, and we accept distance from A and C, and we simply divide it by the distance from A and B, and that's your inverse slurp. Inverse slurp. Is that a good idea, honestly? Right, so because, again, this is a square root. This is a square root. Can you do something with the square root? If you divide one square distance by another square distance, then do you have the same thing? I'll need to think about it too. So fast inverse square root, but this is not an inverse square root, honestly. This is not an inverse square root. So because you have, so this is the first distance right? So, and usually when you just compute the like a dot product, not really dot product, but just like, you know, square x plus square y, you have a square of the distance, right? So then you square that thing and you get the distance. And what we're doing here is dividing it by distance 2, which is also square. So if I just have the square of the first distance and divide it by the square of the second distance, right, the second distance, what I can do with that? So is it, if I take the square root of that, is that the same as this? How does square root work? I don't remember, guys. Are they equal? No, they're not equal. Okay. Yes or no? Okay, so they are equal. Yes, math teacher here. So one of the things we can do, by the way, we can divide one square by another square and only then take a square root, so we don't have to do square root twice, which is a kind of things. Yeah, the square root comes from the dot product, exactly. The square root comes from the dot product. We can, okay, so we can do something like AC, which is the, well, I mean, float. And this is essentially, I need to maybe do something like that. Float dx, and this is cx minus ca. Well, minus ax. I'm sorry, I'm already falling asleep. So this is going to be x and y. Right, so dx and dy. Then the distance in here is dx plus dy, right? And this one is basically, yeah, distance a, but it's a square distance, right? It is a square distance. Might as well reuse the whole thing. So I'm gonna set this stuff like that. So then for the second one, this one is gonna be b, and this is b, but this one probably should have be called c, dc and db, right? So then we divide dc by db and then take a square root of this entire thing, and that should give us the lerp. AC, AD, maybe AC and DB, okay, AC and AB. AC, AB. So is that better? Like, we're calling only square root once. I feel like this is better, but I feel like we can go even further. Right, so if that's a... if that's a thing. Well, I mean, like, the square comes from the dot product. It's not like we originally have d1. After doing this dot product of dx, dy, we get the square of the distance. We don't get it from having originally d1 and then squaring. We originally have this. I just wrote it like that so it's obvious what we're doing. Right, so it's like, I don't see how you can do like absolute value in here. So this is the lerp, and effectively, so what you have in here, you have a value from 0 to 1, but squared. So that's what you have in here. So you need to square root the whole thing. You need to square root the whole thing. So I want to kind of double check that square root of division. Square root of division, right? It's not gonna find me the right thing. Okay, I'm gonna believe you, the chat on this one because it kind of makes sense, I suppose. All right. Square root is exponential, but anyway. So this is the lerp. So what we have to do now is have a three-dimensional one. So we need to have a three-dimensional one. So the three-dimensional one is literally the same. It's just you have additional dimension in here, like so. And this is z. And by the way, I forgot to do that. Plus dz. And this is what we probably have to use for like when we interpolate in one point like to another one. So that's probably what we have to do. All right, so let me try to compile the whole thing because I'm pretty sure I've got some mistakes in here. So do we have, yeah, as you can see, the compiler just told me that I forgot to put t in here. That's kind of the whole point. That's kind of the whole point. So no member t because it's, ooh, yeah, I forgot to put 3 in here. So yep. I hope it is the right thing, but we'll see. So if it's not the right thing, it will be obvious. Okay, so where do we compute the additional clipped points? And the question is, who should report that? We can maybe modify clip line. So we effectively figured out the point between P1 and P2. So this is the point between P1 and P2. Funnily enough, we already have dx, dy, and dz. Look at that. We already have them. Which means we can maybe produce something. Let's actually put parameter t in here. I think this is a cool idea. Maybe we can interleave clip line with inverse lerp. So on top of clipping, you will also have this interpolator simultaneously. And the funny thing is that dx, dy, you already have it. You already literally have it in here, so which is kind of cool. All right, so dx, dy. Funnily enough, by doing x and y like this, you already kind of have the second dx, dy. So you can really embed a lot of things in here, like simultaneously. So here is this thing, and this is gonna be P12, right? So that's basically the square in here. So afterwards we are reusing dx in here. We are reusing dx. But we don't. And this is the second dz, by the way. Speaking of, this is rather interesting. So we already kind of have all of the necessary information. It's just like this is 1, 2. It's just like the problem is the naming. That's the only problem. The problem is the naming. We can maybe keep it like that. Then this is this one. Then obviously this dx and dy and dz are dx 1, 2. Well, this is 1, 2. This is 1, 2. This is 1, 2. And this one, I don't even know how to call that. It's more like dz 1q. If that makes any sense. So it's you have 2 points in here, so you have to think about it like that. P1, q, P2. Right, that's what it is. P1, Q2. So this dx, dy, dz of from 1 to 2, right? And then this is from 1 to q. So this is a delta z for this one, and that delta z is this value. The code is going to be apparent, I think. But anyway, we can replace this like that. But what's funny is that this particular thing, without this dx on its own, is actually something like dx and dy for this one. dx 1q. Something like that, right? Something like that. And so you can actually replace this with dx 1q dy. So that's the final thing. So once you have that stuff, you can have p1q, right, which uses 1q, 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 1q. This is a horrible naming, but I can't name it differently, chat. Listen, like, I mean, if you can come up with a better naming than this, like, go for it. But I can't come up with a better naming. So that's kind of the problem. And at the end in here, so what we do is that we divide the smaller one by the bigger one and take a square root of this entire stuff. So names like this are graphics. Like, I know, like I wish I could name it different, like better. You can tell me that this code is shit, and I will absolutely fucking agree with you. Suggest me better naming then. Like, I hate it as well. Like, this is a horrible naming, but I can't come up with a better one. So, sorry. Deal with it. So we can maybe put underscore in here. I think underscore kind of fixes it a little bit. So, and 1q is something like this, right? So, yeah, so underscore is actually kind of good because it also, like, there's a little bit of a padding introduced by dot, and there is a padding in here introduced by underscore. So this is actually kind of good. Right, so dx, dy, dz for the value. I should actually keep the thing p1, then you have q, and then p2. Right, so dx 1, 2, 1, 2, it's a dx, basically delta between these two things. And then we're computing the square distance of them, like this. And since it's a square distance, maybe it should have been called actually d. Right, so it's a square distance. Might as well call it dd. Right, so because it's a square distance, to emphasize that, so dd. And we do kind of the same for p1q, right, so this dz, and that's the thing in here, right, so, and we know its value in here. And then we're, yeah, so that's good, and I think that's good. Right, so we're combining together clipping and simultaneously getting the inverse lerp of this entire thing, so we can then interpolate this entire stuff. So let me try to recompile the whole thing. So the compilation will now fail because we now have to provide these additional parameters in here. So we'll see how it will go. Right, so there we go. And this one is rather easy, right? So you can just have t1 and you can pass it like this. This is a convenient interface because, yeah, there you go. So now you have to interpolate this thing. So this is clipped 0 to unclipped 1, right? Clip line. Oh, this one is rather interesting. So, and because of that, I need to think how exactly we are interpolating this entire thing. I suppose, yeah, we have to take the color from this thing to this thing and interpolate it accordingly, I suppose. Yeah, so we'll also have to think how this interpolation will go. And this is the second one. All right. So for now, we're not going to be doing any of that stuff. So T1, T2, and this one. Can you see what I'm doing? Yeah. T, and this one is 1, and this one is 2. Okay, so, but we need to interpolate linearly colors. That's what we need to do. We need to interpolate colors linearly. I think we do have some shit for, oh, we literally can have a lerp for the color, actually. So here's the color, and it's actually, you know, bytes, but we can interpolate them. Just, it's gonna be slow, but it's fine. So lerp color, Jesus, color A, color B, float T. Okay. So color lerp and RGB, yeah, that's exactly what I want to do. And we can literally lerp A, R, B, R, T. So this is a byte, but lerp accepts floats, so it will automatically convert it to floats, so which is totally fine. We can reassign it back to A. I think it's fine. RB, RG, RGB, and then oh fuck, RA, like so, and just return A afterwards. Lord. Okay, whatever. It's kind of funny. Okay, so but now I need to like think, what exactly are we interpolating in here? What exactly are we interpolating? So this is the case one. It's this one. This is unclipped 0, right? Unclipped 0, and we just say that, okay, it's that and these two, right? It's that and these two, and these are the neighbors. These are the neighbors, which means that unclipped 0. Oh fuck! We don't know the color of unclipped in here. We don't know the color of clipped in here as well. We just literally don't know the attributes. Fuck. We also have to keep track of them in a similar fashion. What the fuck? Okay, so is there any easier way for us to work with that? I feel like I want to actually work with vectors and colors as an array. That's what I want to do. I want them to be an array. And clipped and unclipped should be indices. Let's try to move away from this thing, and those should become indices. Okay, so, all right. So this is going to be V, and it's 3. V1, V2, V3. There you go. And this one should be C. C1, yeah, so we can replace V with C. There we go. And this stuff, literally index, introducing a little bit of an indirection. I think that's fair. Right, so let's go to the compilation errors now. And it didn't like because it has to be color. Okay, what else do we have? Okay, cool. When I do clipped, this one is interesting. So that means, yeah, these have to be indices. So 0, 1, 2. And this one is 0, 1, 2. There we go. Okay. Furthermore, actually, since this is arrays, wait a freaking second. I can do shit like this, right? So this is now vi, and I'm just passing I in. Damn, broski, that's actually much better now. Yeah, I don't need that. Look at that, and the optimizer will probably unwrap it anyway, so who cares? Yeah, that's pretty cool. And honestly, I want to trigger compilation errors in here. I want to trigger some compilation errors in here, so we don't use these things directly. We don't use this thing directly. So we only should use them as these arrays. You may say that, Zozin, just pass them as an array, but this will trigger a lot of refactoring, which I don't want to do right now. What I want to do right now is to refactor slowly, and like eventually incrementally we'll get to the point where it accepts the arrays. But honestly, it's more convenient if it just accepts these kind of things, at least for now, right? So, but once I'm done refactoring this code, just converting this function to accept array is going to be easy because the code below down there already works with arrays naturally. It already works with arrays. All right, so let's actually go through more compilation errors. So what do we have in here? Yeah, so for this one, I think it's fine to actually iterate it like that. I think it is totally fine. Though, who said so? So let's actually put the private parameters here. We're going to put them private in here. And let's just convert it to the loop. So now we're gonna have loops. So this is that. So we only need these two things, right? And in here, it's vi, and yeah, it's only for x, so that's totally fine. And this one is vi. Yeah. Yeah, we're subtracting, and none of that is needed anymore. It's pretty cool. So that means, yeah, we should refactor all of the code down there to use arrays in here. That's a good idea. All right, so this is correct, more or less. So what else do we have in here? So v1, yeah, that's a good point. And by the way, now I can also use a loop in here. And it's just something like this. It's gonna be something like this. Oh, might as well even make it cool. Does it look cool? Do I look cool when I write 4 loops like that? Anyway. So, what do we have? We have clipped. So here now we have to do a different slightly thing. I feel like we need to use a little bit of an Emacs magic with the regular expressions. So for example, clipped, right, and I have to match this thing and everything inside here, like so. And I think to capture it properly, I have to do it like that. Yes, so this is what we managed to capture. And honestly, do I also capture unclipped? Can I capture unclipped somehow? I think I'm hungry, chat. I think I'm hungry. Right, we should probably start with clipped. How can I make it unclip optional? Does anybody remember? Because un and then just question mark. That's weird, and it also captures. Isn't it just, you know, this and question mark? Be clipped. Well, that's a good idea. So it's a boundary. The word boundary. Thank you so much. The word boundary is a good idea as well. Yeah. So, and what we want to replace this entire stuff with. Honestly, I would like to maybe capture this one, the whole thing, but whatever. Let's keep it like that. So v clipped 1. Boom, 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 boom. Yeah, that's a good one. Thank you so much. All right, so now we're gonna have, let's recompile it and see if it actually fixed the problem. Yeah, so now we only have unclipped one. So let's do that for the whole thing. Can you see, by the way? I feel like you can't see. I'm sorry, YouTube people. I think the chat is gonna be fucked up. I apologize for the chat. But let's quickly do it like that. So you can see now. Boom. Boom, 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 boom. I want you in my room. All right, was good. So let's bring Zuzin back. Okay. So that's pretty cool. Can I realign? There's a relative indent, if I remember correctly. Look, I can do shit like that. So it basically aligns it to the token, the nearest token in the previous line. Look at that. So, yeah, pretty cool. I think I learned that from a while ago, but I don't quite remember. I remember learning it from somebody. Okay, so that should be already working. So let's try to recompile, and that's working. Okay, so we refactored the whole thing. So now it is indirect like that. It is indirect like that. And I still kind of want to rename these things to something. So can I just, yeah, maybe clipped could be CLP. So do you guys have like a shorter name for these indices? And for these indices? Could be something like C, but C is already taken by caller. CI, but CI makes it look like it's an index for the caller. Maybe it's a CLI. CLID. CLP, right? And this is a CLP count, right? So you have CLP and CLP count. So an unclp is going to be unclp. And CLP count. Okay. Why not clip? Okay, let's start with just renaming clipped to clip. Clipped, clip. So is that better? I feel like it's already better. No, it's slightly better, I think. Let's align it like that. Yeah, I guess. And what I like about this kind of stuff on the stack is that it is very small and it is very limited. And I'm pretty sure the optimizer will be able to expand all of the loops, unroll all of the loops, and align as much as possible. It's just like I could have done that myself, but it's too much repetitive work and the code is going to be unreadable. It's better to just describe the intent and let the compiler write the unreadable code. Right, so I'm pretty sure the optimizer will go ham on this code because it has a lot of information. Yeah, clip on clip now reads like an action, so it's kind of bad. We can start with maybe now reducing clip to CLP. Right? Is it better? Nah, it's too much. Yeah, I think calling it like an action is fine because we have a near clip in here. So yeah. One thing I can do, by the way, I can rename count to n. So that's a good one actually. So this one now is more readable. Look at that. So clip n plus. Yeah, okay. So I really like that much better. I think I should stop here. So that is more than enough. Yeah, it's more than enough. Okay, this is a very good code, and I really like that the code kind of naturally evolved like that, right? So I didn't expect it to be this way. All right. So now we are now working with indices. Which means that the corresponding color for this vertex is actually this. Very easy, right? So if I need to know that specific color, now we know. Now I know. So if I remember correctly, in olivec, I did have color mixing. This is not olivec, by the way. Mix colors, yeah. Oh, in this one actually accepts the... It doesn't accept the float, it accepts the freaking fraction. Yeah, it accepts the fraction because in this specific case I was trying to avoid float. Yeah, so here is the mixing of the colors completely in integers. But it doesn't lose any information because instead of passing float, you pass fraction. So now underscores aren't needed. You think they are not needed? Oh, that's a good point actually. That's a good point. Yeah, they're not needed. So the only reason why I needed them is because I wanted to trigger compilation errors in these places. So that's a good point. Can I just query replace v with just v? Boom. And then query replace c with just c. The art of refactoring. The art of fuck. The art of refactoring. So then scripting language developers will never understand the beauty of these kind of tricks and techniques. Yeah. And you don't even need IDE. So do we have a mix color which accepts a float? Mix color, so this is one mix color is 3. No, we don't. Chat, this is disgusting. Oh wait, didn't we develop like a lerp for the code? Yeah, we did. I'm sorry, I'm an idiot. I forgot already. Okay, that's cool. That's cool. So here, essentially, what we need, chat, we need to create color for the queue. So what that means is that, let's call it CQ1, right? And this is basically lerp color, right? So when we lerp in the colors of these two things, and they have to be colors, by the way. So this is the color with T1. That's it. In fact, who said that we need 2 T's? We can just have 1 T in here and reuse it. So here's the 1 T. We clipped this specific line. We got the interpolator and we instantly interpolated color for this one. This is a very convenient interface, holy fuck. Okay, so this is just another T, and in here, this one's gonna be Q2, and this one is an interpolation from 1, like so. Is that a good one? Can I just do it like that? I think it's good. I think it's good. So now, so this, you can literally use the color C and clip in here. So then CQ1, CQ2. Then you can do stuff like that, but instead of this kind of stuff, you do color, and this one is CQ2. Absolute butchering. I figured it out. I figured it out. This is a very interesting puzzle, honestly. Yeah. You only... So the funny part of about this function is that you just have 3 vertices and 3 colors associated with these vertices. You have to consider 3 corner cases. How architecturally do you do that? The easiest way architecturally is to put them in 2 parallel arrays and have 2 separate arrays of indices that indirectly refer to them, and just like generalize it upon that. It is fascinating. It's such a simple problem, yet it requires like a very complicated constructions for whatever reason. Don't you think? You wouldn't expect it to require this kind of mechanisms. I certainly didn't expect it, but here we are doing this stupid ass shit. So yeah. Chill chat. What is going on with the chat? I think, okay, whatever. So here we can do kind of a similar thing. In fact, to have a color, I can just duplicate the line, right? So this is a CQ1. Fuck. Shit. Fuck, damn. And then I lerp the color, like so. This is C. And we don't really have to... Oh, this is so cool. I can literally just transform the new line. This is the color. This is the lerp color. V becomes C. This becomes that. Damn. There you go. So Q1, CQ1, CQ2, and this one is just its original color. That's it. Okay, I'm kind of proud of this function. I'm so sorry, chat, but I feel like I'm proud of this function. I don't know what's up with that. We can maybe even merge these 2 loops together. Who said we can't do that? I feel like we can literally just put them together. Yeah, there we go. So we're doing the transformations and immediately either clipping it or not clipping it. Then we consider these 3 cases, and that's it. All right, so let's see if it compiled or not. It doesn't, because I forgot to put just T in here. So there's a reduplication of T. Is that a good idea to define it twice? But I mean, it's kind of like this part doesn't need this T. Only case 1 and case 2 requires this T. So I guess that's totally fine. I'm a little bit scared, chat. I'm actually a little bit scared. Will it work or will it not work? Let's fucking go. Okay, at least it didn't break. So the first test I'm going to have is, does it look fine? Okay, so at least I don't see the Utah teapot having the debug colors. It does clip through fine, and it doesn't have the debug colors. So that's totally fine. Let's try to go through the floor. It maintains the colors. It interpolates them perfectly. Absolute budgeting. So there's still something wrong with the fog, right? But I think I'm gonna fix that already off screen because I didn't think it's important. The goal for today's stream, fuck. Okay, so something, yeah, there's something wrong in here. Yeah, so what's up with that? Is it something over, yeah, somewhere in here? I'm not really sure what is going on. That seems foggy. Oh, you think it's still foggy? I don't think it's still foggy. It feels like one of the... Yeah, I'm not sure. Z fighting, maybe it is Z fighting, but I mean, who knows? So here it's fine. This is how it's supposed to be. Right. Ah, this is interesting. So at this specific height, it is all right. At this specific height, it is all right. But somewhere here, there's this bug. I'm not really sure. I think I know what's up. Okay. Chat. I just vaguely remembered. So because you need to do near clipping plane stuff. In Olivet's rasterizer originally, I put some hacks. Yeah, so I'm now fighting with the hacks that I put into Olivet's because I didn't really need to develop a proper rasterizer. So there's a function that performs the projection, projection 3D to 2D. Look at that. When the Z thing is negative, it is, well, I think we're doing projection way after. I didn't think it will affect that. I feel like maybe this is what affecting all of that, but no, I don't think that's what affecting it here. So we have this kind of stuff. All right, let me try to remove these hacks. Will they actually fix? Yeah, doesn't fix it. So there's something. It is picking like a black color for this one. It's just picking a black color for this one when it's somewhere here. Though when you do it like that, it is fine. So I'm not sure what that. It's actually clipping really fine. Weird. I'm not even sure how to debug that. We're creating a new triangle as part of the clipping. No, yes we do. Yeah, we actually do. By the way, let me go maybe back to before we had clipping. Did we have the same problem? Right, so this is code without today's changes. Though, one of the things we probably want to do is remove the fog. Right, so this is the code at the beginning of the stream. I'm removing the code from the fog from the original thing. So it has the same problem, though, kind of. Though it starts, you know, freaking out when the actual clipping needs to occur. But this is literally the same problem before our code. So it feels like maybe the problem is somewhere else. I think this is the problem from somewhere else. Let me remove the fog and yeah, I'm gonna do it like that. So, and this is the new code. This is the new code. The problem still persists, though on a slightly different level, right? But the if you stay on this specific Z, it's not Z, it's Y. It's kind of fine, right? I'm going back and forth. And there's no glitches anywhere in here. Only when you go a little bit higher, it starts to have this kind of stuff. So it has nothing to do with near clipping plane because this is the bug that originally existed. So it's kind of similar, but slightly modified now. So here's the plan. I'm already streaming for 2.5 hours. I'm gonna investigate this bug off screen, and I'm gonna make a footnote for the session explaining what this bug was, right? So because I'm already a little bit tired, so I don't want to go into this rabbit hole in this specific mental state, right? So I'm gonna have a little bit of a rest, and I'm gonna claim today's session success because I literally achieved what I wanted because the clipping working, right? So we're doing this kind of thing, so it's totally fine. And with the teapot, with the Utah teapot, I can go through Utah teapot and it's fine. I can go back, I'm going backwards. Right, so clipping through the Utah teapot again, and everything's fine. All right, the bug is mutating. Yeah, it's kind of interesting about graphics is that you have small bugs, but then you can make some changes to some other part of the code, and the bug is mutating. All right, that's pretty cool. So let me just commit whatever we have in here. Implement near clipping plane, and yeah. That's pretty cool. So that's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you all on the next recreation programming session with Mr. Azoizer. Love you all. All right, this is the footnote of the session, and I figured out what it was. It was a bug originally in the code base. I didn't introduce it, and it was with how we mix the colors, right? So I just screwed up the order of some operations, nothing particularly special. So let's go to maybe, I think it's render end. So this is where we do all of that stuff, and here's the code that is responsible for blending, and it's just like I had to do these operations in a slightly different order. So if I'm basically interpolating between three colors, and when you are interpolating between three colors on the screen coordinates, right after the projections, you have to be a little bit careful because you have to interpolate it in a perspective correct fashion. But since you're on a screen, you cannot really do that in a perspective correct way. So you have to take into account the Z value of each individual vertex as you interpolate. So you basically have to interpolate by reciprocal of Z. Right, and it's just like I had to do that in a different kind of order, and that actually fixes the problem in here. So let me recompile the entire thing, and now it should actually work more or less. So yeah, so it's not reproduce anymore. Look at that. This is so satisfying, actually. I really like that. So yeah, we can have a floor, and it's just fine. So there's no problems in here whatsoever. I can go through the teapot. It's a little bit slow, of course, but it's all unoptimized. Also, the chat suggested pretty interesting idea with interpolating 3D or multi-dimensional vectors. Not really interpolating, by doing inverse lerp. So let me actually say it was a clip line. Maybe I'm gonna go into the vector H in here. Yeah, so essentially, instead of interpolating by along the vector, you can just interpolate by one of the components of the vector, honestly. So let me actually open my paint, and maybe I can draw that. It kind of makes sense, right? So I didn't think about that during the main session. So it's a very interesting idea. So just a second, let me do that. Right, so you have 1 point. Let's consider 2D space because it's easy on a 2D plane. Just a sec. So let's connect these two things, and there we go. So you can do inverse lerp along the line itself, which requires square root and stuff like that. But honestly, you don't really have to, right? So if you just project all of the 3 points, on, for example, horizontal axis, right? So this is going to be that, and this is going to be that, and this is going to be that. As you move along this vector, you also kind of moving linearly along this axis too, and also along this axis as well. So instead of along the vector, you can just do that by one of the components, right? So the only problem that you may encounter is when the vector is, for instance, pointed up. Right, so you can't really interpolate by X anymore, but you can just pick Y instead. In fact, it probably generalizes to multiple dimensions. You can just pick the component with the biggest difference, right? So do inverse lerp by that, right? And this is a kind of a cool idea, which basically gets rid of the square root, which is rather expensive operation. So I suppose this is what we're going to be doing in the game. And in fact, we can even try to do it right now. So we have interpolation already built into clip line, right? So this entire interpolation already built into clip line. And honestly, we already kind of have the differences between components in here calculated, right? So dx is the difference of x between p1 and p2, and dx1q is the difference between p1 and q. Right, so instead of doing this thing, I already can just assign t to dx. I need to pick the smaller one, right? Smaller over the bigger one, dx 1, 2, right? So, and that already gets rid of the square root. And let's actually see if it works or not. I need to recompile the whole thing, obviously. I need to recompile. So, does it? Yeah, it seems to be working. Yeah, it seems to be fine. Right, so it's all interpolating properly, more or less. Right, so this is the green one, so yep. Yeah, so I think this is a pretty cool idea. And I'm gonna add a support for basically picking the biggest component a little bit later off screen. So that's it. That's everything I wanted to say. Thanks everyone for watching. See you all on the next recreation plugin session. I love you all. Mwah.